Okay, in this video we're going to find the inverse Laplace transform of this big vector valued function. So this is something that you might come across when you're solving a system of differential equations using the Laplace transform. So let's see what we have. We have a scalar multiple out front of 1 over s times s minus 1 times s plus 1 times s minus 2, and then we have a 2-entry vector. We've got s cubed minus 13s squared plus 8s plus 10 up top, and 3s cubed plus 13s squared plus 14s minus 12 down in the bottom. So for ease of notation, I'm just going to set the entire interior of this equal to capital Y vector, as you would if you were using this to solve a differential equation. Okay, so now the next thing that I want to do is the following. I can take all of this stuff that's inside, which I've called Y vector, and rewrite it in the following way. So I can still take this term out front, so s times s minus 1 times s plus 1 times s minus 2. And then the next thing I'm going to do is factor this into a sum of 4 vectors that are being scalar multiplied by certain functions. And so we're going to write s cubed times the vector 1, 3, because that's the coefficient of x cubed in the top entry and the bottom entry. And then we'll do plus s squared, negative 13, 13. So again, that's the coefficient of the s squared term, plus s times the vector 8, 13. Oh, sorry, 8, 14. And then finally, plus the vector 10 minus 12. Okay, and now we're going to take inspiration from how we usually solve inverse Laplace transform for scalar valued functions, and that is rewrite this using partial fraction decomposition. But in this case, our coefficients for the partial fraction decomposition will be 2-entry vectors. So we can write it like this: 1 over s times vector A plus 1 over s minus 1 times vector B plus 1 over s plus 1 vector c, and then finally plus 1 over s minus 2 vector d. Okay, great. Now we can take this equation and clear all of the denominators, and that'll give us a simpler equation that involves polynomials instead of rational functions that we can use to solve for a, b, and c. So in other words, I'm going to multiply both sides by this denominator. So on the left-hand side, it's just going to cancel this denominator, and on the right-hand side, I'm going to have a big polynomial expression to write out. Okay, so let's get at it. So we'll have s cubed times the vector 1, 3 plus s squared minus 13, 13 plus s 8, 14 plus 10 minus 12. I missed a minus sign there. Good, and that's going to equal, and so look, for this 1 over s term, we're going to have s minus 1, s plus 1, s minus 2. So if you multiply that out, you'll get the following: s cubed minus 2s squared minus s plus 2, and that's going to be multiplied by vector A. So let's just reiterate what this is. So this is s minus 1, s plus 1, s minus 2, because those are the terms that don't cancel when you multiply by this vector A. And then we have this is plus, so our coefficient in front of vector B will be s cubed minus s squared minus 2s. So that'll be in front of vector B. And then in front of vector C, we will have s cubed minus 3s minus 2s, so that should be 3s squared. So that's going to be in front of vector C. And then finally, in front of vector D, we're going to have s cubed minus s. Okay, great. And just as a quick reminder where all of those come from, so this term is the product s times s plus 1 times s minus 2, because that's everything that does not cancel when you multiply by vector B. And then this one down here is s times s minus 1 times s minus 2, again, because that's what does not cancel when we multiply by vector c. And then finally, this is s times s minus 1 times s plus 1 for the same reason. Okay, good. So now from here, I'm going to clean up the board, and I'm going to bring this equation to the top, and we'll move on to the next step. Okay, so I've brought that equation up to the top, and it looks like kind of a monster, but it won't be that hard if we just pay attention to all of our bookkeeping and work through it carefully. Okay, so what we're going to do is take the coefficients of s cubed on either side of the equation, the coefficients of s squared, the coefficients of s, and the constants on each side of the equation, and that will allow us to solve for this vector a, b, c, and d. So let's look at the coefficients of s cubed first. So notice on the left-hand side of the equation we have vector a plus vector b plus vector c plus vector d, and then on the right-hand side of the equation we have the vector 1, 3. Okay, now let's look at the coefficient of s squared on both sides of the equation. So here we have minus 2 times vector a minus vector b minus 3 times vector c, and then there's no vector d, and so that's going to be equal to, let's see, minus 13, 13. Now we have the coefficient of s, so here we have minus a, and then minus 2b plus 2 vector c, and then finally minus vector d, and this is going to equal 8, 14. Sorry, that should be negative 14. This got switched when I copied it over. Okay, great, and now our constant. So on the left-hand side, we only have 2a, and then on the right-hand side, we have 10 minus 12. Okay, so let's put an orange box around this. This is our system of vector equations that we need to solve for vector a, b, c, and d. So now let's notice that immediately we can see that vector a is equal to 5 minus 6. So we can hold on to that for later. So we've solved for vector a. So the next thing that we can do is plug this value for vector a into these three equations and simplify. So we're going to plug it in here, here, and here. And if we do that and rewrite things, let's see what we get. So we'll get the following three equations. So we'll get vector b plus vector c plus vector d. So that's now equal to 1, 3 minus 5, 6. So that's going to be minus 4, 9. Okay, good. And now again, here we can add 2a to both sides, but then let's also negate that while we're at it so we don't have these hanging minus signs out here, and that will give us b plus 3c equals, and so let's see, that's going to be 3 minus 1. Okay, so to reiterate, what we did right here is we moved this 2a over and then we just changed the sign on everything. Okay, and then finally plugging into this last one down here, so we will again add a to both sides, but then we'll negate so we don't have this hanging minus sign out front, and that's going to give us twice b minus twice c plus d equals minus 13 and then 20. So now we have these three vector equations. So now let's see what we can do with that. Now notice what we can do is subtract these two from each other and eliminate the b. So let's do that. So here, let's put that, and then we're going to take this guy and this guy and subtract them. Good. So we'll do this second equation minus this first equation just to keep the leading term positive. So notice that's going to give us 2 vector c minus vector d equals, So let's see, that's going to leave us with 10 minus 7. Sorry, 7 minus 10. Okay, but now we're in luck because notice this twice b has a minus 2c plus d, but now we have 2c minus d left over there. So what we can do is take these two guys and add them, and we will eliminate the c vector and the d vector. So let's see what we get when we do that. We will get twice vector b is equal to the vector given by minus 6, 10, which tells us that vector b is minus 3, 5. Okay, so now let's go ahead and put a box around that. And we can move on to finding vector c and vector d. Okay, so what we can do from here is plug this value of vector b into this equation. And notice that's going to give us, well, let's see. We're going to go here and then there. So that's going to give us vector minus 3, 5 plus 3 times vector c equals 3 minus 1, like that. But that gives us 3 times vector c equals 6, and then minus 6, which tells us that vector c equals 2 minus 2. Okay, good. So we've got an expression for vector c. And then finally, we can plug this value of vector c, let's see, maybe into here, and we can solve for vector d. Well, really, we can kind of plug it anywhere, but let's go ahead and plug it here. And let's see what that gives us. So we're going to have 4 minus 4 minus vector d equals 7, 10. So sorry, that should be minus 10. Great. But that's going to tell us that minus vector d equals, so let's see, we've got 7 minus 4, which is 3. And then we have negative 10 plus 4, so that's going to give us negative 6. But that tells us that d is equal to negative 3, 6, because we need to change the sign. Good. And we finally have all 4 vectors related to this partial fraction decomposition. Okay, good. So I'll clean up the board now that we've found these 4 vectors, and we can finish the whole thing off. Okay, now we're ready to finally finish it off. So our goal was to find the inverse Laplace transform of this vector-valued rational function. So look, it's pretty complicated, but we broke it down using partial fractions as follows. And so I've written this using the linearity of the Laplace transform. So notice I have the Laplace transform of 1 over s times this vector a, and then so on and so forth. So the inverse Laplace transform of 1 over s minus 1 times the vector b that we calculated, the vector c that we calculated, and the vector d that we calculated. Now, we're going to use this following fact, which we proved on a previous video, that the Laplace transform of e to the at is equal to 1 over s minus a. So what that means, if you take the inverse Laplace transform of 1 over s minus a, you get e to the at. And that's all we need to take these inverse Laplace transforms. So notice this is going to be e to the 0t, in other words, the number 1. So that's going to give us just the vector 5 minus 6. And here we're going to get e to the t minus 3, 5. Here we're going to get e to the minus t, 2 minus 2. And then finally here we're going to get e to the 2t minus 3, 6. And that is us successfully taking the inverse Laplace transform of this big vector valued function. Okay, that's the end of the video.